Hey, this is Leach with Simpson Math, and in this video, I'm going to be going over two example problems of how to do a one sample z-test for a population proportion. The focus of this will be using p-values, and my primary audience for this is my online statistics course using the Larson 8th edition textbook, because I'll be using two examples directly from that. But, of course, anyone can hopefully glean a few things or two. So let's go ahead and let's take a look at this first example. It says, a research center claims that 24% of adults in a certain country would travel into space on a commercial flight if they could afford it. In a random sample of 1,200 adults in that country, 27% say that they would travel into space on a commercial flight if they could afford it. At alpha equals 0.01, is there enough evidence to reject the research center's claim? So just one little caveat, just note, I'm using my textbook for my online course is Larson's 8th edition. If you watch some of my videos from my online stats class, you might have noticed me complaining about that textbook. I'm not a big fan of it. And this is one of the big reasons why they do this weird thing about about the claim, and it just, I don't know, it just feels bad and weird to me. Mainly it's just confusing. But it's the hand that we're dealt, so we're gonna make the most of it. So that's partially why I'm making this video, just to try to make a little bit more sense of it for y'all. So I've highlighted some things, as you can see. And what I like to do when I first see a problem like this is to process my given information just to see what I have to work with. So for this type of question, especially my online stats class, you're going to need to be aware of what is the claim. Because that makes it that's a driving force as to how our hypotheses are going to be written. So it says, kind of spoon feeds that into you, we have, it claims that 24% of adults in a certain country would travel into space if they could afford it. So that is our claim. So notice here we're talking about a proportion. This is 24%, but when we do mathy things, instead of doing percents, we tend to do proportions. So I'm going to use all this that I've highlighted in blue to define what my P is. My P is the true proportion of adults in a certain country who would travel to space in a commercial flight if they could afford it. So I'm looking for that true proportion. I don't know what that true proportion is, but that's the proportion I'm kind of putting to the test. So someone has claimed that 24% of adults would do that. 24% as a proportion is 0.24. So that is my hypothesized value, my hypothesized P. That's that claim. So notice, since it's a P equals 2, kind of spoiling it a little bit, and that's my claim. That's my null hypothesis. I'm kind of keeping my purple is one highlight for my claim, and then the light, that teal cyan color is for the me defining what P is. So what are some other information here? So this is a random sample of 1,200 adults. So 1,200 adults is my sample size. It's also important and nice that it is a random sample. Then we see that it says 27% say that they were traveling into space. So they contacted 1,200 adults, and 27% of them said yes to their question. So my sample proportion, someone claims, this researcher claims 24% of all adults would agree to this, but when I took a sample, I found 27% said yes. Is that weird? It's 3% more than what I was expecting, but is that weird? That's the idea. That's the whole idea behind stats. Is this is what I saw, but this is what I was expecting. I didn't get what I was expecting. Is that weird? And so that's kind of what this is evaluating. So p hat being my sample proportion, is 0.27, or of course my 27%. Oh, I lost my little percent ditty. There we go. And then lastly, we have that alpha is 0.01, or as a percent, that would be 1%. So let's talk a little bit about these hypotheses. So like I said, since the claim is that P is 0.24, the way that Larson 8th edition defines the alternative or the other hypothesis, because sometimes the claim will be the alternative, is that it will be the complement. So in this case, since I'm claiming that this is a number, it is exactly 24%. The complement is, well, it's just not 24%. In my face-to-face classes, I play I might try to maybe find a link to it and link to it in the description. But it's an SNL sketch of a commercial of I think it's called Alexa Silver for senior citizens and Alexa for senior citizens, and like a running tagline they have throughout it is the senior citizen going, well, I don't know about that. So that's the idea behind it. Someone makes this claim and you go, well, I don't know about that. And so you think, well, I think it's actually probably going to be this thing. So we're going to see if we have evidence to actually reject that and come down to this alternative. So the reason, again, the reason why this is not equal to is because my null hypothesis is equal to, and then it's the complement of it. One thing to remember is that the hypothesis, the null hypothesis will always have the equal to part. In some other books, some other stat classes, they will say that it's always equal to. We'll see in a second where it might be a less than or equal to or a greater than or equal to, but it always will have that equal to part. So keep that in mind. So if the claim has anything to do about an equal to moment, our book is defining that as the null, even though that's weird. I don't like the whole claim business. I think it's just confusing. Anywho, I'll try to stop rambling about that. I won't. Okay, so let's take a look at our conditions. Now, obviously, I'm doing a little bit much. I'm doing a little bit extra. I'll show y'all what the question on my lab looks in just a second, and you don't have to do all this. Me being the stat teacher that I am, I want to make sure that we're doing an appropriate job. So I have the conditions, I have the math that we're checking, but I'll show you technology in a second, so you can kind of skip over this math if you need to. But I want to make sure that you're aware that it's not just magic black box giving you the answer. So our conditions, things that we can do to make sure that we're doing the right test. If we had more tests, we'll end up in this course kind of just seeing 5 different tests, but it's good to kind of be able to process this. So first, is this a random sample? Yep, we're told it's a random sample. Up here, random sample. Then the biggie, and this is the one that my lab will make a big deal about, making sure that you check it from a time or two, is NP and NQ. NP and NQ have to be at least 5 according to Larson. The previous video talked about how that's stupid, and it should be really 10. This 5 is a little bit too small, but acceptable in stat worlds. But we really, most statisticians prefer at least 10, even though this is still really small. In most cases, especially in academic world, we typically have big numbers, and we see that clearly they are. We have 288 and 912, and both of those are clearly bigger than 5 or 10. And then lastly, our book doesn't make a big deal about it, but some other people might. So just putting this out there, it's called the 10% condition. We understand that if I'm sampling without replacement, because I'm not going to ask the same person twice if they want to go to space. I'm sampling without replacing. So technically that messes with some independence here or there. And I don't need it to enter into my calculations, really, as long as my sample size is less than 10% of the total population. If my sample size is less than 10% of the total population, then the differences that the independence would make are way down on the many decimal places that away, that we don't have to worry about it too much. So then these 3 things check out, so then we can perform a one sample z-test for population proportion. So here's the math behind this on how we can get our z-score, the z-value, and then the p-value. So first, let me just talk about our formula here for the z-score. So this z-score should feel very familiar from when we did z-scores back in the day. So you should remember that z-scores are some x minus like your mean divided by a standard deviation, or we can be a little bit more generic and say it's an observed value minus an expected value divided by some sort of standard deviation, just to be a bit generic. And that's what we have here. What am I observing? I'm observing this statistic, this p hat. What am I expecting? What's my average? What's my mean? What's the center of this normal model? That's going to be my hypothesized p. I'm not sure if our book uses that p null, but if I had to kind of make a little formula here, I would say that this is p equals p null, where this is the, notice that's a subscript 0, and this is a subscript 0. So we're referencing that. That's the hypothesized value, the hypothesized number of that parameter. Instead of just p, those words, is that p null number. So the value that I'm observing minus the value I'm expecting, That's also the center of the normal distribution here. And then our formula for the standard error. Back when we did the confidence interval, we saw this, but instead of P null and Q null, it was P hat, Q hat. That was because the center of the confidence interval is P hat. Here, the center of this, we're assuming this is true. We're assuming the null hypothesis is true until we have evidence otherwise. So since I'm assuming that's true, I'm assuming that this is P. So P is the center of my distribution. So P null is what gets used in the calculations for the standard error. So P null times Q null, well again, Q null is 1 minus P null divided by N. So here I'm plugging in my numbers. These numbers and the highlighting comes from what we saw above, what I highlighted. So here's my P hat. There's that P null. P null again. Q null is 1 minus the P null to get 0.76 and then divided by my sample size. And the last of my sample size is 1200. You could throw this all in the calculator at once. If you do, especially it's real nice on Desmos because you can see it exactly like this. If you're going to use it in something like an 84, make sure we're using the math type fraction. So hit alpha y equals to be able to get your numerator nicely. I can show you that in a second if I remember. And then, so when to do my numerator, so again, I got 27 versus 24%. So I'm 3% higher than what I'm thinking it is. Is that enough to say it's weird? Well, this would produce a z-score of 2.433. So in most cases, probably. But let's take a look at our p-value and our alpha. So two things are going on here. So first up, whoa, it's going drunk on me. Okay. There we go. So first up, here is my z-score that we just found in my normal curve. And when I find this area, this little bitty area above this, which I did for my normal applet, I see that's 0.0075. But since my alternative is a two-tail alternative, I would have been just as surprised if I would have been down 2.433 standard deviations instead of above 2.433 standard deviations. And because I didn't care enough to specify that I was interested in seeing if it was less than or more than or whatever, I kind of have to pay a little bit of a penalty by doing this double tail because again, I'm testing the claim of equal to, so it could be done on either side. So I'm looking less than the negative version of my z-score, which is basically the opposite sign, and it's of course also the same. That's why we can get away with just doubling 2 times that shaded region, 2 times that probability. And I got 0.0150, which notice is our probability outside from our Rossman chance applet. All right, of course you can also get this using an 84, using the normal CDF as well. All right, so just in conclusion, our p-value of 0.0150 is larger than my alpha of 0.01. To be honest, when I was preparing this video, I was just kind of going, it was like boom, 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 boom. I wrote that this was smaller than that because I kept going because it was, oh yeah, that's pretty small. But it didn't actually make my comparison to my alpha. 0.0150, a p-value, that is typically pretty small. But for some reason, the problem wanted us to have a good amount of evidence before we rejected this, in order for us to reject this null. For some reason, maybe a billionaire was trying to see if they were wanting to invest in this or not. So they were putting a lot on the line. So we were, so since our alpha is a pretty small alpha, 0.01, this is not enough evidence for me to reject the null. This number would have to have been less than 1%, and it's 1.5%. So it's just a little bit bigger than our alpha. So I'm going to fail to reject the null. I'm going to fail to reject the claim. So then we have, oh, I forgot to go back and say do not. I made an edit. Oops, let me do that right now. And I'll just do it in this color so we see. We do not have, there we go. We do not have convincing evidence that the true proportion of adults in a certain country who would travel to space in a commercial flight, if they could afford it, is not 0.27. So notice here I have 2 sentences. The first sentence is about the first hypothesis, the null hypothesis. So it's about whether we reject or fail to reject the null hypothesis. So my p-value, what is my p-value? compare it to my alpha, and we either reject or fail to reject the null. The second sentence should be about the second hypothesis, the alternative hypothesis. So we either have or we don't have evidence for the alternative. Now I know I'm saying this, and in my online class, I'm never going to see you write a sentence ever. You're just often filling in the blank or checking kind of a multiple choicey type situation on the MyLab platform. So I wish I could see you be able to go about these things, but nonetheless, it's helpful for us to see what is kind of typically expected among stat students on how to be able to write these conclusions. So let's talk about this, and then in a second I'll show you, we'll just look at how this question is worded directly on MyLab. So again, I have two sentences. The first sentence is about the first hypothesis, the null hypothesis. So we're going to check our p-value, state what our p-value is. We're going to compare it and we're going to state our alpha and compare it to say it's either the p-value is bigger or smaller. And then based on it being bigger or smaller, we'll reject or fail to reject the null. Then our second sentence is about the second hypothesis, the alternative hypothesis. And we either have or we don't have convincing evidence about the alternative. Notice if we're doing this properly, and sometimes the pre-made concluding sentences in MyLab are a little bit jank. If I'm being honest, you can tell I don't really like this book. But we need to make sure that we're discussing about our evidence. We need to make sure we have non-deterministic language. I did not prove that P is 0.24. I mean, I kind of have evidence. I mean, kind of it feels like it might not be, but I didn't have evidence to say that it's not. We're kind of in a weird no man's land. So I did not have enough evidence to be able to leave, which did not prove that P is 0.24. And even if I did reject the null, that would not mean that I have proven that the null is false. It's just I have evidence. There is some sort of wishy-washiness here. If you think back to when we talked about type 1 and type 2 error, how just based on kind of dumb luck or based upon differences in our sample size or the effect size and all these things, it's possible to make type 1 or type 2 errors. So that's why we need to be saying things like, based on we have enough evidence to say this or not we've proven something or we've determined something. So make sure we have non-deterministic language. I'm a visual person, and so maybe this might help you. This is what I see in my head whenever I'm writing my hypotheses. So first, what's my p-value? Then is this p-value bigger or smaller than the alpha? If it's smaller than the alpha, rather, we're going to reject the null hypothesis. There's a cheeky little phrase that I teach my students. It's if the p is low, reject the hoe. It rhymes. So if the p is low, reject the hoe. And also with that is we never accept the hoe. We never accept the null hypothesis because that's the thing that we're assuming to be true. If I accept the null hypothesis, the joke is mama don't want to meet no hoe. If the p is low, we reject the hoe. We don't bring the hoe home to Thanksgiving dinner. You don't bring that type of individual home to meet mama. You might have your side piece, you might have fun with them, but you either reject them and are done with that, or you will fail to reject them and kind of maybe entertain that for a little bit longer, but you never accept them. You never put a ring on them, right? So if the p-value is low, we reject that hoe. And then what do you have to do if you rejected the null? You got to go to somewhere, and you got to go to the alternative. So you have strong evidence for the alternative. So I'm going to switch back to my main camera because I'm going to talk with my hands for a second. Anyway, I keep saying. So anyways, what I like to do sometimes, another way to think tangibly for a second is, I imagine that my pencil is the null hypothesis, and my Apple pencil, the white one here, is the alternative hypothesis. And here's me, here's my two little legs, and I'm standing on the null hypothesis. So this is what we're just kind of hanging out of the null hypothesis because this is what we assume to be true until we have evidence otherwise. And then if I reject the null, this null goes away. It's gone. And now I'm standing here wildly coyoting it a little bit, desperately needing to go somewhere. And by golly, I'm going to grab onto this alternative hypothesis with all my strength because I was just in air up here looking for some ground. And so, by golly, I'm going to grasp onto that alternative hypothesis with all my might. So if I rejected the null, I got to go somewhere. I can't just be in the void. I go to the alternative, right? So that's what we just did there. Now the other path is this. If my p-value is larger than my alpha, that is not enough evidence to reject the null. So we say we fail to reject the null. We don't accept. We fail to reject the null. then we do not have evidence for the alternative. Because typically that's why we're doing the test. We were wanting to show the alternative is true. That's why we're doing that. So we typically in our second sentence, we're going to say that we either do or we don't have evidence for the alternative. Again, I'm going to go back to my kind of pencil situation here. So if I'm standing on the null hypothesis here, and I don't have evidence to leave it, I'm wanting to leave this, I'm wanting to get away from this null hypothesis and get to the alternative, but I can't because I don't have enough evidence to leave it. So I'm just gonna kind of take a seat. I'm just gonna kind of kneel down, maybe just kind of sit like this, sit with my feet dangling off, or maybe just kneel down on it. I'm just gonna hang out here. I'm not gonna grasp on it for dear life because I've confirmed that it's true. I'm just gonna kind of hang here. I don't have reason to leave, but that doesn't mean that I'm proving that it's true, right? So two things here with the pencil thing and this picture. I have one choice that you make. It's not even a choice. One thing to look at. What's my p-value compared to the alpha? Is my p-value small or large? If my p-value is small, I'm going to reject the null. Null's gone, and I got to go to the alternative. I got to grasp onto it for dear life. If my p-value is large, then I can't leave the null, so I'm just going to hang out here, right? Sometimes students get a little bit confused because they feel like it's three decisions. They feel like one decision or one thing to compare is my p-value big or small? Do I reject or fail to reject? Do I have evidence or not have evidence? I do not have three choices or three decisions or three different yes or no's to make. You have one yes or no to make. One decision, one thing to determine. Is my p-value big or small? If it's small, then you will reject the null, and then you will say that you have strong evidence for the alternative, or you have evidence. If your p-value is really, really small, then we can maybe throw on some sort of qualifier like strong evidence. If my p-value is big, then you will say that you're going to fail to reject the null, and then you will say that you do not have evidence for the alternative. This blank here is my alternative in context, like here. So instead of just saying we do not have convincing evidence that, and me just writing HA, we need context somewhere in these two sentences, so it's best to put it here. So we do not have evidence, convincing evidence of my alternative hypothesis, but notice I'm putting it in context. All this in blue is just a regurgitation of what I said earlier that P was, and then is not 0.27, which is this information up here. Here's my P, and it's P is not equal to 0.27, my alternative hypothesis. All right, so I hope that helped a little bit more big picture. We're gonna look at a second example. We're just gonna start it. I'm not gonna do much of the work, so you see like that's the end of it. We're just gonna start it just to see how the hypothesis is. Whoops, focus. There we go. And then we will journey on into looking at technology. So this is a humane society claims that less than 70% of households in a certain country own a pet. In a random sample of 700 households in that country, 462 say they own a pet. At alpha equals 10%, or sorry, at alpha equals 0.10, is there enough evidence to support these societies' claim? I didn't highlight it this time, but last time I highlighted that in gray and said that tells us that that's a hypothesis test. I forgot to talk about that. Notice here, we are not estimating. This question is not asking us to make an estimate, to estimate what P might be. We are proposed a claim. A claim was presented to us, and we're putting that claim to the test. So that's why we are testing this claim. We're seeing if we have enough evidence to support the claim. So what's the claim here? So it claims that less than 70% of households in a country own a pet. Notice it says less than 70%, not less than or equal to, not at least or at most, or any of those words that might imply like an equal to at it. So it's just less than. So if that's my claim is that less than 70% of households in a country own a pet, that is my alternative. I know that's my alternative because there's no equal to part with that, right? And again, what is P? P is that true proportion of households in a country that own a pet. All right. So since I'm going to go ahead and jump the gun a little bit. Since this is my less than, and that less than is my alternative, the complement to that would be something that is greater than or equal to. So my alternative here is greater than or equal to 0.7. Now, if my face-to-face class or my business stats or someone else, maybe in AP stat land is watching this, we don't say this. We don't say greater than or equal to. We just say equal to, because if I'm wanting to show that it's less than 0.7 and my results come back bigger than 0.7, well, I don't have any business trying to do the test. So we just kind of stop. But Larson, 8th edition, and older editions, they do use this, which is fine. It's kind of covers all the bases. So that's how that works, that greater than or equal to. All right, so sorry if you heard background noises. The trash is getting picked up outside, and for some reason they were honking. Okay, so other things we have, our sample size is 700. That's my N. I wanted it to be green because my p hat was green, but this isn't p hat. This is it says 462. That's not a percent or a proportion. This is my number of successes. So I put in this lime green, but after I wrote it, I realized it was hard to see on my screen. So I put a gray background. My iPad, it looks real nice, but when it's coming through on the screen, it's blindingly bright. So notice this is my number of successes. This is not a proportion of successes. So I need to probably calculate my proportion so I can do math with it. So let's kind of take a look at that. So if 462 own a pet out of 700 people who asked, that sounds like my proportion right there. But if you want to see a formula for it, recall that p hat, my sample proportion, is my number of successes divided by my sample size. Well, my number of successes was 462. My sample size was the 700. I just did a little bit of division in my calculator over here, and I got 0.66. Exactly. It terminates quite nicely, so p hat is 0.66. We were told that alpha is 10% or 0.1. I think we've already covered our hypotheses there. So obviously our sample size is big enough. We're told it's a random sample. We're gonna go through the same math. We'll get a z-score, we'll get a p-value, and we'll be able to move on. One note here, since this is a one-tail test, a left-tail test, so we can actually get away with less kind of evidence, and it's a little bit easier because we're not having to double our p-value. And on top of that, the alpha is 10%. It's not requiring a lot of evidence. Give me just a second. I need to click some buttons. I want this one. I want this one. I think that's it. I click this button. Shablam. Okay, might be a little bit small, but this is the this is from 4.7.13 in our Larson textbook, section 4.3, question 13. So it's the same question, but you can see kind of the breadcrumbs that the question has. So identify the claim. The claim is that this says 24% of adults in the country would travel into space on a commercial flight if they could afford it. So this is identifying kind of what P is and what that claim is. Since that is an equal to claim, that's my null hypothesis. So we're picking this one here, that is P is 0.24 versus P is not equal to 0.24. So let me show you how we can quite easily use our Rossman chance applet, our theory-based inference applet, to be able to get this. So if you're in our Rossman chance list, it's down here in the bottom right corner, theory-based inference. Earlier you saw me use, or you just saw a screenshot of the normal probability calculator. That's here, moving my mouse so you can see it. But we're going to be down here in the bottom right corner for theory-based inference. All right, something that is super optional is, in a second, I'm going to turn on this test of significance button. And you see how this is pi? That might freak some of you out, but it's a valid substitution for p instead of pi. But most statistical educators opt out of using pi because that freaks a lot of us out, because we've been trained that pi is the ratio of the circumference over the diameter of a circle. So if you want it to see p instead of pi, just come down here at the bottom right corner. It says use p. It'll load in a slightly different one that has p instead of pi, but they're effectively the same thing. So if you don't want to go through that rigmarole, then don't. Just leave it at pi. All right. So just like in our confidence interval, you could switch to a mean or a proportion. Since this is a proportion situation, we're going to leave it at proportion. And we only have one sample. Chapter 8, we'll see two samples where I'm comparing two different samples and their proportions. So we just have the one. So I'm going to put in my observed data values that I saw earlier. I could scroll up and look at it, but I'm just going to look on on my iPad. So I have my sample size is 1200. They did not give us the count, which would be the number of successes that the number of people who said, the number of people who said yes here. but they did give us my sample p hat, my sample, my sample proportion, which is 0.27. So I'm going to type in 0.27, just click out of it, and it's going to automatically calculate the count by just doing 1200 times 0.27 to get 324. If you want to press calculate, you can. It'll kind of give you a bar chart here to kind of see there's my 0.27. And now let's look over here on the right-hand side. If it's not, you need to check test of significance. And then let's take a look at this. So I need to put in what my hypothesized value is. Right now, you see how this normal curve is way over here, way away from the rest of things? Well, because this is the 0.27 that my p hat was, and this right now it thinks that p is 0.5. They're just using 0.5 as the default. There's just a 50-50 chance. It's a coin flip. So we need to change this p to what the p actually is, which is 0.24. So just change this to 0.24. When you change one box, it'll automatically change the other box, but you do need to press calculate for it to fix things around. But it's saying that my p-value is kind of really, really big, and this is shaded really, really darkly because it didn't change my alternative. So this is just like on the normal probability calculator. This is a button you can toggle through, but actually has 3 toggles. So it can be less than, greater than, or not equal to. So it's just a toggle. The more I click it, the more it flips through those 3 options. Less than, greater than, not equal to. We already determined that our alternative hypothesis is not equal to. You saw as I was switching through that, the picture was changing. One reminder, it is a feature, not a bug, that I could click and drag this thing around. I think it is. I think I can. Maybe if it's a one tail. Well, maybe I can't. Maybe it's on something else. I swear I've gotten it to move before. If you ever actually click and drag around here and it moves, then that was on purpose, but oops, you might have changed your problems and then go back and fix that. Thought it did. Maybe they took that off. Anywho, so our standardized test statistic is this. Z is 2.43. If you need an additional Z, if you need additional decimal place, you could, if you put your mouse over it, it'll hover and it'll pop up another decimal place. Actually, I asked Beth Chance of Rossman Chance to try to give us more decimal places if they could, and so she graciously added this little hover over so we can get another decimal place. They were a little hesitant because they weren't sure about how many decimal places of accuracy, so they didn't want to make it a big obvious thing, but it is there and it should be able to be correct because also MyLab allows a little bit of tolerance as well. Then in addition, we have our p-value is 0.0150. That's great. Don't worry about the continuity correction. That's acknowledging that this distribution is a little bit discrete, but we're not doing that. We'd use kind of like the binomial distribution-ish thing. One other, a few other like shortcut things that if you're needing to show some work. If I look back at my work, let me go back to it. If you look back here, we can see that the observed difference here is 0.03, which we know. And we see that our standard error is just 0.012329. Let me go back to this thing. Look in the top left corner of this graph. Do you see this SD is 0.012? That is the standard error. That is the value in the denominator. So you could, if you needed it to be able to estimate this, to use this for some reason or show the work for it, you can just simply do your 0.27 minus 0.24 to get the 0.03 divided by this 0.012. That's pretty nice. If you really needed to check that out. So here's our z-score of 2.43 and a p-value of 0.015, which is exactly what our applet gives us. So notice how that's nice, that's quick, pretty painless. Let's take a look at the conclusion here. They're a lot less wordy than what I had us write down a second ago. I really like what I have, of course, but we'll just get by with what this says here. Let's try to make sense of this. Remember that this book loves this claim thing to a fault, and it kind of makes your conclusion weird, because here it says we're going to fail to reject the null hypothesis. Cool, because my p-value is low. I wish we would explain that, but my p-value is lower than my alpha, so that's why I'm failing to reject the null. Sorry, I misspoke. My p-value is bigger than my alpha. My alpha again being 1%, 0.01, and this is bigger, so I'm going to fail to reject the null. And this is, there is not enough evidence to reject the researcher's claim. So the reason why I don't like this is it's redundant and it doesn't mention the alternative hypothesis at all. So I'm going to fail to reject the null, which is the claim. So there's not enough evidence to reject the claim, which is what the first sentence said anyway. I don't like this, but we deal with what is. So it's a little bit dumb when the null hypothesis is the claim, because in the way that Larson wants us, because then we're not talking about the alternative. And that's really kind of why we want to do this. So it's like, I have my null, I don't have enough evidence to reject the null, so I can't even say that this alternative is true. We can't get to that point. But hopefully that makes sense there, because the next question, the claim floats. The claim is now in the alternative. So that's why our concluding sentence is going to be a little bit different. So now let's take a look at doing this one. So if my P is, so remember this one is about the households owning a pet. So I'm just going to press reset. So that way most things will go away and we'll reset. My sample size is 700. This time I was not given p hat. Now we did calculate p hat on our own, but I'm kind of pretending I didn't do all the work by hand a second ago. If I was just answering this question, I see that it says 462 say they own a pet. So I'm going to put 462, and I'm just going to click out of it somewhere. And when I do, notice I get a p hat of 0.6600, which was what I got, 0.66. So it does that calculation by doing 462 divided by 700 to get this number. So that's pretty nice. All right, again, I need to adjust my p over here to be 0.7. Now, one thing that you need to be mindful of is this applet is one of the many statistical technology things that assumes that the null hypothesis is always just equal to. Don't stress about it. It agrees with what ours has. Larson textbook is just a little bit more specific in a way where it deals with a complement. So it might be, so in this case, the null is greater than or equal to, but it does have the equal to part. And my what's important is I need to, for the calculation part, fix my alternative to be less than. When I do, if you need to press calculate, but really spinning through this will take care of spinning through the alternative options is also kind of a version of a calculate button. So when I do, I get a standardized test statistic of negative 2.31, which is what we have right here, and a p-value of 0.0105. So this does round to 3 decimal places to 0.011, but I believe if I double check, I bet it would accept, I have a little green tag here saying that it has more than one number that it would accept, and also has a little bit of range tolerance as well. This might have been calculated from using 0.31 instead of using maybe 0.3, negative 2.31 instead of negative 2.309, or a more accurate value. But it will accept these, there's more accurate values. There's sometimes more things you see behind the hood. At the end of the day on this question though, what is this p-value? This p-value is about 1%. What's my alpha level? My alpha level was 10%, 0.1. Well, my p-value is smaller than my alpha, so that means that is enough in the threshold, enough in the area for me to go, oh wow, that is enough evidence for me to reject the null. It's not likely that it happened by random chance based on how much evidence that I need. So I will reject the null hypothesis and then say that I do have evidence for the alternative being that the true proportion of households in a certain country that own a pet is less than 70%. So here's how my lab wants us to answer this. So what am I going to do about the null hypothesis? Well, my p-value is lower than my alpha, so I will reject the null hypothesis. The claim, though, in this case, the claim is in the alternative hypothesis. If it's in the alternative hypothesis, I'm either supporting the alternative or not supporting the alternative, or having evidence to support the alternative or not, versus that my claim was the null, we either have evidence to reject it or not. So since this is about the alternative, then we can say there is enough evidence to support that alternative, which in this case is the claim. So I hate how our book does this, where this claim floats around. It's a little bit weird. So if they ever watch it, hi, I hate your book. But especially this section. But anywho, so that's that. Let's take a look at how to do this on on an 84. Let's make the screen be a little bit bigger. Here we go. Okay, so I'm going to go through these same questions that we did a second ago, but just do it in an 84. So just like how the Rossman chance applet has tests built in, this does too. So I'm going to press the stat button. Then I'm going to arrow over to tests. Here is where my intervals and my tests live. Tests are in the top half. If you keep going, you'll get intervals. So I'm going to do the one prop for one proportion z test. FYI, if you keep going, if you were back in last chapter, that would be the one prop z int right here. But we're doing the one prop z test. Press enter. All right. And this is very similar to what we just saw in the Rossman chance applet. So the p null is what would be on the right hand side. So that's that hypothesized value. So this first one is 0.24. So I'm going to say 0.24. X is my number of successes. So in that first example, you do have to kind of backwards calculate your number of successes, which I don't have in front of me. So you can't just type in a p hat. So this one, they told us it was 0.27 was my p hat. So I'm going to do 0.27 times 1200 and get the 324. So we do have to do that ourselves. And then my sample size was the 1200. Our alternative was a not equal to. I'm not going to draw it. I'm just going to say calculate. So notice I've answered 4 questions. What's the null? And then how many successes over how many attempts? 324 over 1200 will get us the p hat. And then what is our alternative? Let's press calculate. And then, so it's reminding you that your alternative was that the proportion does not equal 0.24. Then z is this 2.43, which is what we see. That this p is not the proportion p. This p is our p value p. I know that because it doesn't have a hat and it doesn't say prop. Or if you maybe on like an Inspire, it might have a p null. I'm not sure. I don't remember. So here's our p value. Notice the 3 decimal places, it is this number. And then p hat is 0.27, which we had already calculated, which was actually given to us anyway. So they're kind of giving you back your givens back, so just kind of letting you see that p hat. All right, now let me do 7.4.15. So I'm going to press second quit to kind of clear this. Go back to stat, go over to tests, down to 5, or I could just press 5. And then there's stuff already here. I'm just going to type over it. 0.7, enter. This time they give us my number of successes, 462, so I don't have to do any multiplication, over my sample size of 700. But this time my alternative is not a not equal to, it is a less than that we determined. Less than this p null being this p null right here. This p null is the same. And then calculate. Again, this prop is my p null. The proportion is less than 0.7. Here's my z-score. Let me scooch this down. It's above my head. There we go. So this is, here's my z, negative 2.31 right here. Notice if I'm rounding to 3 decimal places, it does round down to 3 decimal places. The Rossman chance applet might have been terminating a rounding or something, and it was rounding up, but it's all good. I promise that it would accept it. That's why these little green tags have some acceptable other values that are within its rounding tolerances. So this is 0.010. So that's how that works. All right. Oh, I think I remember why I was confused. It's because Rossman chance appropriately rounded to 4 decimal places, 0.0105, which is correct. That's a correct rounding for 5. But if I was to take that rounding and round to 3 decimal places, because I was only provided those 4 decimal places, I'm going to then round up. But ideally, I should round down. That's why it's, just a little bit of intermediate rounding, but I promise it would be accepted. There's an appropriate tolerance there. All right, so I think I covered everything that I wanted to cover. Yeah, so I hoped that this helps. You got to see the Rossman chance applet in action. Got to hear me gripe about the claim. I promise I hate it too, but hopefully it should help enough with some practice in this section and the next. Throughout the rest of the course, you'll see that show up. And this structure of this test is going to be similar. In other chapters, it'll be a t-test instead of a z-test. So it's kind of all that same thing. So, like I said, I hope this helped. If you have any questions, as always, let me know, and I'll see y'all in the next one. Bye bye.